Okay, this is my second take at the video. The first one got really long, so I'm going to try to stay a little shorter here. The degrees of freedom for the independent t-test is a combination along the same principle as what we had for the simple t-test. So we have this n-1 for the first sample. We have an n-1 for the second sample. We add all of this together and it gives us the total degrees of freedom that we're going to use to find the critical region. So in a sense, we have everyone that's in the combined sample minus 2. We're subtracting 1 for the first sample, 1 for the second. So we're basically adding everyone that's in this sample, subtracting 2. Again, we touched on this in number 1. The independent t-test has a null hypothesis that the means are equal to each other. You would not necessarily have to have this. You could say a null hypothesis that the means differed by 5 or 10 or 12. For example, maybe you have good reason to believe that female IQ is 10 points higher than male IQ on average. So you might have female IQ mean minus male IQ mean equals 10. But in, I think, all of the tests that we'll be doing here, this is going to end up being 0, which says that the two population means are the same. Okay, with Cohen's d and r squared, we're starting to get into a different type of significance. So over here, when we had the the t-test, when we had the p-values, the critical region, we're looking whether or not we reject the null hypothesis. All of that is statistical significance. So we're saying, is there a difference? Yes or no? Is there a difference between the population means? When we get into Cohen's d and r squared, we're starting to look at practical significance, which says, how big is the difference? And does that difference matter? Is it a meaningful distance? So one thing that's a little bit different between these two types of significance is the first one, the t-test, the p-value, the statistical significance, is only based on mathematics. So we're using mathematics to determine a yes or no question. When we get into the practical significance, we do have math as part of it. We calculate how big, how many standard deviations, that's what this is doing right here, saying how many standard deviations is our effect, how far away were the two means, how many standard deviations away from what we would expect them to, or from no difference. And the r squared is how much of the variation is accounted for by the treatment that we were looking at, or whatever the difference was between the two populations. So these are mathematical components of the practical significance, but we're also going to pull in common logic, common sense. So for example, maybe a small effect size in terms of a drug that reduces tumor, some kind of malignant growth, that would be very, very practically significant. It would have a lot of value practically. Whereas something with maybe you had a small effect size and it was about changing the length of your toenail, that probably wouldn't have as much practical significance unless, I don't know, there was something cultural about toenail length in the society. So the practical significance here is going to look how big of an effect was there, and does that effect matter? Does that big of an effect matter? And you're going to have to bring in non-mathematical logic into that. The last thing here is just the homogeneity of variance assumption. And we haven't talked a lot about assumptions yet. Everything we do in terms of an inferential statistic test is based on assumptions, and we want to know, can we reasonably meet these assumptions? So one of the assumptions is that when we're looking at two different samples from two different populations, we want to know, are those population variances the same? Because if they're not, when we take a pooled, let's see, where was it? Right here. When we look at the pooled variation, if the two variations in the two populations are not the same, it's kind of like we're trying to take two different estimates of two different things and combine it, and it's like comparing apples and oranges in a sense. So we need to know that the two variations are reasonably equivalent, and that's what this Hartley's F-max test is. And in terms of the mathematics of it, a couple pages earlier, there's a little area in the text that goes through it step by step.